Our final exam, as always, is scheduled for 3 hours. It's going to be on Tuesday, I believe. Is that right? Can anyone confirm that? Tuesday of over 1 week from now, a week and a half from now. Is that right? Yeah. No. Oh, if you look on our class website, it says the final exam, section 1 is on one day, section 2 is on the other day. That's because you are all section 1. Yeah, it's not a two-parter. You are all section 1. Don't come to the other. Don't come to the other one. The exam is scheduled for 3 hours, but I'm gonna make it about the same length as our ordinary other 2-hour exams. You can have the whole 3 hours, but I'm not trying to make it super long. I don't want to grade a super long test anyway. So you'll have 3 hours to do it, but I don't expect it'll take you that long. But you can have it if you want.
Is it in this room?
Yeah, it's going to be in this very room at that time. I don't remember the time. It's on our class website. You are all section 1. All right. Any other logistical matters? No calculators, as usual. Let's talk about it then. We can talk about anything that you see on the paper. Maybe I'll just refresh our memories. Really, the topics are Euler circuits, Hamilton circuits, and spanning trees. That's really all there is to it. When I said Euler circuit, that also includes Euler path and the minimum duplication circuits and minimum duplication paths. We can do examples of any of those things. A lot of these questions just say find an Euler circuit or something, and on the other page is the last page and back of it. I just put a bunch of graphs, and I tried to put these in columns here. So the first column there is about Euler circuits. See if you can find an Euler circuit in each of those, or say that it's not possible. These pictures are a little small. You might want to copy it sort of onto your own paper when you're actually working on these, but I didn't want to make them too big for the purposes of this cute little handout. Anyway, what should we discuss? We got about a half hour. We can talk about whatever you like. Yeah?
Can you go over Euler paths?
Sure. Euler paths, and let's talk about Euler paths. Euler paths are very similar to Euler circuits. So remember, a Euler circuit exists when all degrees are even. Euler circuits are much easier to deal with than Hamilton circuits because it's really easy to look at the graph and just tell immediately if there's an Euler circuit or not. It happens when all the degrees are even. If I just give you a graph at random, it probably does not have an Euler circuit because probably some of the degrees are not even. But anyway, Euler path exists when, anybody remember the rule for this? Similar but slightly different? Remember? Yeah, it exists when all degrees, I'll say all degrees are even except 2 odds. And an Euler path means you start at one place and end at another place, and you use every edge in the graph once. All degrees are even except 2 odds. And then the 2 odds, in that case, the 2 odds must be the starting and the ending point. So, for example, I'm going to try to draw a graph which actually has an Euler path in it. How about this? I think that, no, that doesn't. I'm also, how about that? I think this one does have an Euler path. You look at the degrees. So a question like this, I would say, does it have an Euler path or not? If so, find it. If not, tell me why not. You look at the degrees everywhere. Here, this is 2, this is 4, 2, 3, 4, 4 here, 3 here. I see 2 odds, right? The 3 and the 3. The rest are even, so it does have an Euler path. It has an Euler path. And can you find it? Yeah. I hope you remember the basic idea for finding Euler circuits or finding Euler paths. First of all, you have to start at one of the odds. So maybe I'll start at this 3 down here. That's my starting point. And you can more or less do whatever you want. Try to cover up all the edges. Make sure that you never cross over an edge, which is a bridge among all the unused edges. So right now, everything is an unused edge. I want to choose these, make my choices to kind of keep all the unused edge together so that they never have a bridge connecting like 2 islands of unused edges. I'm feeling pretty good about this so far because so far in my path, all the unused edges are still like all over here in a lump. You just never want to separate the unused edges into 2 separate parts of the graph. Maybe I'll come down here next, up this guy, and I think I can just go around the square and I'll be done. There are many ways that you could have done this, so this is not the only possible way to draw the Euler path, but that is a way. Yeah?
For the 2 odds, do they have to be the same number, or could they be like a 3 and a 5?
Yeah, they're not always going to be the same number. Yeah, in this example they were, but it doesn't always happen. Yeah. So that's a Euler path. You remember how to do the minimum duplication thing? It's similar, but a little more complicated. You want to try one of those? Yeah, why not? Let's talk about minimum duplication circuit, and then we can talk about minimum duplication path also. So how about maybe the, I'll make it a little different. Let's try this. Let's find a minimum duplication circuit. All right, and then after we do that, here I'm going to make another copy of this, and we'll also find a minimum duplication path in a moment. So what you want to do for a minimum duplication circuit is similar to an Euler circuit in that you want to use every edge, but you want to do it with as few edge repetitions as possible. So the first thing to do is look carefully here and decide which of the edges am I going to have to duplicate. And you decide that based on the degrees again. I'm just writing all the degrees here. That's a 5 in the middle. Which of these edges am I going to have to duplicate? Focus on the odd ones, and hopefully you remember this. You want to kind of pair them up by adding in new edges, but the new edges you add in have to be, they have to just be copies of existing edges. So I'm first of all, I focus on these odd ones, right? And then I want to try to pair them up by duplicating some existing edges and trying to think of a good way to do that. Oh, I missed one. Yeah. I was a little worried there. Can we? How many edge duplications do we need in order to pair them up? There are 6 of them. So the best we could do is sort of 2 by 2, make 3 little groupings, and I can do that by duplicating, say, this edge here, this edge here, this edge here. The purpose of that is that it changes these odds to become even, right? Like these 2, they used to be 3s, but if you add this edge here, they now become 4s, and now they're each even. So what that means, I'm not done at this point. Some people, when they did the homework, they just like stopped here. You're not done. Your actual answer consists of a circuit that you draw in here, just like I did, just like this one here. Only it's going to cover every edge and perhaps repeat some of them. So I'm going to now draw a circuit in this one where I'm going to go over each of these 3 edges twice. That's the idea. Maybe I'll do it on a fresh picture. I'm going to have to make another copy of this. Going to put it all on the screen at the same time. This is my fresh picture. Okay, since I'm doing a circuit, it doesn't matter where you start. You can start and end. You have to start and end at the same place, but it could be anywhere. So I'm just going to try and draw my circuit as usual, trying to cover every edge without making any bridges, without crossing any bridges anywhere, and keeping in mind that I'm going to end up duplicating this edge, and this edge. So maybe I'll go down and come right back up. That edge there. All right, that was my first duplication. And then I'll go around here perhaps. As I go, I'm trying to keep in mind where are the ones that I didn't hit yet. They're all over here. You want to keep them all together in one piece. Don't split them up into two pieces because then you won't be able to cover both of the two pieces. Continuing, maybe I'll go up and back this edge because I know I had to repeat that one. And I'll go around here. For the most part, you can do whatever you want. You just have to make sure you don't split apart the ones you didn't cover yet. Here we go. I think that looks good. And I might ask you on the test, like, indicate to me specifically where your duplications are. I mean, you can tell if you look closely, but they are. I have three dupes, and they are, right there, and right there, right? Those are my three edges which I duplicated. And that is the minimum number of edges you can duplicate here. I mean, I had 6 total odd vertices, so there's no way that I could have done this with any fewer than 3 edge duplications. All right? Any questions about that one? That's minimum duplication circuit. What about a minimum duplication path? That means you can start and end at 2 different places. The effect of that, what that means in practice is you look at the odds, again, are these 6 vertices. But since I only want a path and not a circuit, I don't have to make them all even. I can leave 2 of them as odds and make the rest even. So that means I only am going to require 2 edge duplications in this case. Let's say I want to duplicate that one and that one. But I will leave this one like it is. That's because when you're making a path, you can afford to leave 2 odds and make the rest even. So I'm going to end up duplicating these 2 edges, but I will leave that edge as just 1. And I have to start at one of these and end at the other one. So maybe I'll start at 3 and do something a little like this. I'll go down and back here. That's my first duplication. Come down here. Again, there are many ways you could draw this circuit in there. What happened? Oh yeah, I'm going to end at the 5. I got a little worried there. There we go. That is a minimum duplication path. And I ended up duplicating 2 edges, right? 2 dupes. That was here and over there. All right? This is a minimum duplication path. I hope that that's sensible. Any thoughts about that one? I know I said it many times before, but please don't just like put little arrows on the graph. Don't do it. Sometimes people are like, "Oh yeah, here's my path," like that. Boom, 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 right? And they just like draw a bunch of arrows. Now these arrows don't make any sense at all. But if that's all you give me, there's no way I can tell what you mean. Where are you going from one step to the next? Like if you're going to start here, did you go that way first or that way first? Who knows, right? I know this looks a little cuter and tidier than what I did, but sometimes, you got to be cruel to be kind. You have to make this look a little bit messy in order for it to be sensible when somebody else is reading it. All right. What else shall we talk about? Yes, I just for the purpose of not handing out a lot of stuff, I wrote up the answers and I'll put them at the website. I hope that's acceptable. Just because most of the answers was like me drawing on all of these things. So check it out. they'll be there for you to see the answers. What else? Yes?
Could you do the find a Hamilton circuit of minimal weight?
Mm-hmm. Sure. That actually is that is like what we did on the quiz. You know, on the quiz I said use the nearest neighbor, and then I said use the sorted edges. So I hope everybody did that more or less right. That part A right there, I didn't actually say how to do it, but there's a clue that I said find the Hamilton circuit of minimal weight. If you really want the best one, the only way to do that is brute force. The nearest neighbor and the sorted edges only get you something which is pretty good, but not necessarily the best. So in that example, you have to do the brute force. Maybe I'll just, and it's not hard to do, although in a big example, it will take you forever. I'm not going to ask you to do brute force on anything bigger than 4 vertices like this. But I'm just going to make up numbers here just so that you can keep the one on the paper to do later on. Mm-hmm. All right, I don't know how this is going to go, but let's say this is A, B, C, D, like that. And let's do the brute force. You have to write down all possible circuits, all possible Hamilton circuits, and just starting from wherever. So maybe I'll just do it as if I'm starting at A. Then what they are, I'm going to make a complete list of all the ways you could just write out those letters in some other orders, starting and ending with A. So one is A, B, C, D, A. You could also do A, B, D, C, A. All right, those are the only 2 that start with B in the second position. I could also start with C in the second position in 2 ways, A, C, B, D, A, or A, C, D, B, A. And then I could start with D in the second position, A, D, B, C, or A, D, C, B, A. Those are all of the options. And for each of them, we just have to add up and see what the total weight is. So A, B, C, D, A. I look at the numbers over there. A to B is 1, plus B to C is 2, C to D is 1, D to A is 3. I think that's actually probably going to be the minimum one, but we have to check them all to make sure. 1 plus 2 plus 1 plus 3 is 7. And then A, B, D, C, A, that would be 1 to A to B. B to D is 4. D to C is 3. No, D to C is 1. C to A is 5. So this adds up to 11. The next one, A, C, B, D, A. You go A to C is 5. It's going to be 5 and 2 and 4 and 3. That's a particularly bad one. 7, 11, 14. All right, I think I did that right. The tour was just walking by, and all I could think of was like, I got to add these numbers right. For once in my life, I think I added them correctly. Because they don't know that mathematicians are not necessarily good at adding. The other 3 actually are all, each of the other 3 is going to be some reversal of one of the ones that we've already done. So it's not really necessary to think those through. But so this one here, A, C, D, B, A, if you read it backwards, is A, B, D, C, A. That's this one here, right? So this one is 11. They will have the same totals as when we did them the other way around. A, C, B, D, A. This one backwards would be the 14. And then this one backwards would be the 7. And so my conclusion, the 7 is the best. The best is A, B, C, D, A. Or if you prefer, A, D, C, B, A. Those are the same thing in reverse. This is really the only way to find the best, or the circuit of minimum weight. You have to do it this way. What else? Any others?